check numerically yourself. Okay? Now, this was for moving average order 1. And the moving average order 1 we did was for Y1, which is here. Now, the exercise B2 says, derive the moving average 1 for spectral analysis for Y2 obtained by, by the autocorrelation of Y2. Now, look at here. Since the moving average order 1 has to have a 0 in 2, the only coefficient that is saved is only the coefficient in 0. So, at the end of the story, even if the autocorrelation has been computed for a moving average order 4 here, okay, so the process of Y2 is moving average order 4, is impossible to be modeled as a moving average order 1 because the coefficient of the corresponding filter comes to be 0. Okay, so it's similar to the other exercise, the previous exercise here. You see where I have the coefficient in 1, which is 0. And since the coefficient in 1 is 0, so the moving average order 1 does not exist. Okay? It's impossible. So, here. So moving average of V2 is the same as exercise 1309. Now, derive the autoregressive spectral analysis for Xn. Xn is the sum of the two, okay, of the two autocorrelation because the two random processes are uncorrelated, mutually uncorrelated. And because of this, I can calculate the autoregressive spectral analysis order 1 and order 2 by using the Euler-Watt. Now, conceptually, what we are doing with autoregressive spectral analysis. Okay. 'Is we are applying here a linear predictor. Okay, so we apply on Xn a linear predictor of order 1 or 2, depending on the case. So I'll tell you two possible linear predictors. Okay. This is 1 plus A1Z minus 1, or 1 plus A1, 1, 1, 2. Plus A1, 2, Z minus 1 plus A2, 2Z minus 2. And here I have epsilon 1 n and epsilon 2 n. Okay? And this is the prediction error. So what I need to do is for autoregressive spectral analysis is the following. I assume that I don't know the mechanism how it is generated. I take the autocorrelation that, as I was commenting with them, we are using the analytic autocorrelation. So we are using the ensemble, the autocorrelation computed with an infinite number of samples. In the case of stationary process, so we are ideally using the system, and then by the autocorrelation the ensemble autocorrelation, we are computing the autoregressive spectral analysis, which means that assuming that I know the autocorrelations of Xn, my goal is to compute the corresponding pole system. So I'm saying that I want to calculate out of that a generation mechanism that is composed by one random process, which is filtering this one by a filter that is one pole, and is giving out, as you know, an x prime n, which is not exactly as xn, but is giving the same power spectral density, or at least approximately the same, or equivalently, which is equivalent. I postpone, rather than model this, I postpone to xn a linear predictor such that I make the prediction error to be as small as possible by searching for the optimal linear predictor, optimal in the minimum mean square error sense. By searching for the optimal linear predictor, I get as the output, as a solution, okay, A11. This A11 is the optimum pre-widening, which is cancelling optimally a possible modeling of the random process characterized by one pole. So, which is totally two equivalent representation. I can either say, I want to look at this generation mechanism where I know Xn. In practice, I don't know Xn. I say it again, I don't know Xn. I know only the ensemble value of the autocorrelation of the Xn. Okay? So, but assuming that I know the autocorrelation, not the ensemble, but the true one of the autocorrelation of Xn, then what I do is I take this autocorrelation and I calculate the optimal linear predictor. This optimal linear predictor is the optimal widening filter. Is trying to flatten the spectrum. Is trying to widen the random process Xn. This is the auto-regressive spectral analysis of order 1. The order 2 is carried out in a similar way, except that I use a linear predictor order 2, which is with the goal of widening. So trying to have epsilon 2, which is the output, which is the prediction error, to be as wide as possible. Wide means uncorrelated. Okay? Ideally, if epsilon 2 is perfectly uncorrelated, okay, I get perfectly the power spectral density of Xn, because it's perfectly uncorrelated. Now, the reason why I can do this trick is because, you know, they are ruled by the same equation, which is a Euler-Walker equation. So Euler-Walker is ruling the linear predictor, is ruling the autoregressive autocorrelation of the spectrum, is ruling the autoregressive spectral analysis. Now, analytically, my goal is just to solve two sets of Euler-Walker equations. Now, Euler-Walker equation for 1, so for autoregressive blue color. For autoregressive order 1, the Euler-Walker equation that I have to solve are, so it is Ry1 k plus A11, which is the first coefficient, Ry1 k minus 1 is equal to it's equal to sigma square epsilon 1 times delta k. Okay? So I need to write a system of two equations into unknown. These are the unknown. Okay? So I'm using Euler-Walker because I go from Ry1 to the coefficient and sigma epsilon. Okay? This is why I use the Euler Walker. Okay, for autoregressive order 2, I do similarly, so I do ry1k plus a1 2 ry1k minus 1 plus a1 a2 2 ry1k minus 2 is equal to, I have no room to write, is equal to sigma square epsilon 2 times delta k. Again, is a Euler-Walker equation, which has to be solved now, this time, with respect to the 3 parameters. Luckily, it's linear, so I need just to write a system equation for that. So, with respect to moving average, is using a Euler-Walker equation. Okay. Now, as a general, so since we are using Euler-Walker, remember that, let me write here, remember that Euler-Walker, just for your mnemonic. Remember that Euler-Walker is put in relationship Ry, like in this case, but Ry1, so it's Rk, is put in relationship the Rk with the coefficient of the filter, okay, and the power. So, now if I have the coefficient, if I know the filter, let's consider this case. And this is the excitation in sigma squared. And this is Ym. Okay? And similarly, I can calculate A of Z depending on the set of coefficient to get epsilon. And that, coincide with that one and with the power sigma squared. Okay, now, so if I know the filter, if I know this one, I go there. That means, knowing the filter, I want to calculate the autocorrelation. This is what you have been doing till the intermediate exam. In the intermediate exam, I give you the Euler-Walker to calculate the autocorrelation, usually, okay? Which means, I give you this, and you calculate the autocorrelation there. Okay, Euler-Walker. Now, in spectral analysis, and similarly in linear prediction, I compute the opposite way, which means I know the autocorrelation there, and I want to find the optimal linear predictor, or I want to find the filter which is perfectly pre-widening the random process y1. That means that I know the autocorrelation. This might be known as the ensemble. Ensemble means the ideal case. Okay? The ideal, or perhaps I know for some reason, I know the autocorrelation analytically, okay? It might be possible. Okay? So this can be known by the ensemble, or this can be known by the sample estimate. This probably might be the case in practice. Okay. So I know this. If I know this, I make the spectral analysis, which means computing that one. Okay? Once I get this estimate, that in that case I calculate as A12 and sigma epsilon. Once I know this one, I know the power spectral density. Because the power spectral density is modeled by a system with poles. This is the conceptual picture. If you like the conceptual picture, this is the conceptual picture. Now, let's make, and let me see, this one or the other. I can do only one. Let me do this one, it's more esoteric. Okay? It's less trivial. I have let's make let's change the subject, okay? We are on periodogram. So let's read it. I have a noisy signal, blah, 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 which is composed by a superposition of two sinusoids. One at the frequency of pi divided by 200, and the other is pi divided by 2. With amplitude A1 equal 1 and A2 is equal 110. To be estimated, okay, which means, are unknown in the estimation process, so I don't know A1 and 2, okay? So I generate the model with A1 equal 1 and the A2 equal 110. A2 is smaller than A1. The amplitude is smaller. Now, Wn is a zero mean Gaussian process with power is wide. I forgot why. With power 10 to the power 3, and the phi1, phi2 are random terms due to the sampling process. Can be neglected. So phi1 and phi2 are phase of the series. Now, compute the power spectral density of SW of the process. So, goal is to compute the power spectral density of this guy. Now, what is the power spectral density of this one? I'm saying the true one, not the periodogram, okay? So the one that, I'm searching by the periodogram. Now, so let's start. So the power spectral density, now what I do is compute the autocorrelation of X. And the autocorrelation of X is the autocorrelation of the sinusoid 1 and the autocorrelation of the sinusoid 2. Okay? Plus the autocorrelation of the noise. Okay? Because phi1 and phi2 are uncorrelated each other. Okay? Then for this reason I can calculate the autocorrelation. So the autocorrelation is A1 squared divided by 2, and then it is cosine of omega 1k plus A2 squared divided by 2 cosine omega 2k plus sigma squared W multiplied by delta k because it's y. Okay? So this, if you forgot that, how to calculate, okay, see previous exercise. So I compute by the Fourier transform, and so the power spectral density is equal to A1. So I have a cosine generates plus minus, 1/2. And so it is A squared divided by 4, and it is delta of omega plus minus omega 1. Okay, so I have 2 delta. Then I have a plus A2 squared divided by 4. It is a delta of omega plus minus omega 2. And then it is plus sigma squared W. Okay? That is by the Fourier transform. But I don't know if I told you, when I use this notation, when I write as delta x plus minus x0, this notation stands for delta x minus x0 plus delta x plus x0. It's just a notation that I'm going to use to write compactly. Okay? So the power spectral density, now let's plot it, compute the power, compute, and I suggest, whenever I suggest to sketch it, okay, to represent graphically. Minus pi, 0, pi. Now, omega 1 is, where is it? Pi divided by 200, so it's very close here. Omega 1. Omega 2 is pi divided by 2. 2, omega 1. Okay, now the power spectral density is 10 to the power 3, and the amplitude is very small. So I mean, the power spectral density, let me sketch it. It's very big noise. Okay, that is 10 to the power 3. And then superimposed there is A1 is 1, so it's and then omega 2 is very small. Okay, so this is what we get. Okay, this is the true power spectral density. So the sinusoid, I mean, looking at the individual sinusoid, the sinusoid number 2 is very small compared to the noise, okay? So which is smaller there. The sinusoid number 1, it's a little bit bigger, but I mean, okay, the area of the amplitude, the area of the delta is A1 squared, so A1 is 1, which is 1/4. And this one is a 1/10, so it is 10 to the minus 2 divided by 4. So I mean, it's very small compared to 10 to the power 3. Okay? Nice. Okay, good. So this is the power spectral density. Now, define the periodogram and its mean and its variance for 1000 observations. So in total here, I'm assuming that n is equal to 10 to the power 3 in my periodogram. Okay? So that means that, I have the variance, and if I don't do anything, the variance of a simple periodogram is, let me try to sketch it, using a mild color. Okay, so the variance of periodogram is that big. Okay, just to sketch it, okay? We saw it, we saw last time, but it's something very big, okay? So that is the periodogram on n equal 10 to the power 3, which is a simple periodogram. Okay, so there is no way I can see the sinusoid. Sinusoids are, tiny with respect to the white noise. W. Now, and by the way, for n equal 10 to the power 3, the periodogram might be biased. Now the question is, I want to calculate the bias in this case. Now, I know from the theory that if I calculate the bias is the expectation of the periodogram calculated, okay, by convolving the true, which is equal to the true periodogram, to the true power spectral density, convolved with the simple square. So the bias is evaluated So the bias analysis is that the expectation of the periodogram is equal to the true power spectral density, which is the one that we just plotted, convolved with a certain window, which is a Bartlett, the Fourier transform of the Bartlett, okay? Circular convolution on a period of 2 pi, and then everything sampled in 2 pi divided by n multiplied by k. This is the bias. Now, what is Sx? So Sx is, so writing, it is sigma square x convolved with Wb omega plus A1 squared divided by 4 delta. So it is delta omega plus minus omega 1. Well, delta. So if I make WB omega convolve with the delta omega plus minus omega naught. This is equal to WB omega plus minus omega naught. Okay, so this is the property I'm using. So this is equal to WB, which is a single square, omega plus minus omega 1, plus I have A2 square divided by 4, omega B, omega plus minus omega 2. Okay. Once done that, omega equal to pi divided by n multiplied by k. Okay. So for the first time I do step by step. Now, what is this convolution? How can I calculate this convolution? I can calculate this convolution in space. So calculating in space, in space is time. Calculating in time, this is equal to sigma squared W times delta K multiplied, okay, multiplication is because convolution becomes a multiplication in time, okay, multiplied by what? By a triangular window that has a length of n. But you know, this is a delta and this is a triangular window. So the multiplication with that gives me sigma squared W times delta K. Because I'm multiplying by a triangular window. Triangular window in the center is 1. Okay? So that means that because of this, I mean, for the white noise, there is no bias. So because if I go back, this is equal to sigma squared W, okay, times delta K. Time, that's it. Then, you know, I have plus. Now I have A1 squared divided by 4. Then I have a W Butler, omega plus minus omega 1, computed in omega k. And then I have a plus A2 squared divided by 4, Butler, computed in omega k plus minus omega 2. Now, what does it mean? It means that, you know, the white random process is never biased. Okay, so periodogram for white random process is never biased. Now, in order to avoid the bias, so this is the bias. So to avoid the bias, okay, so what I need to do is I need to put omega 1, which is equal to pi divided by 100, to be equal to an integer number of period of interval 2 pi divided by n. So it is k1 multiplied by 2 pi divided by n. And similarly, omega 2, to avoid the bias for the other, it should be equal to pi divided by 2 equal to k2, which is an integer, times 2 pi divided by n. So I solved this equation constraining k1 and k2 to be integer. And I can find the condition for that. Okay? So the condition is easy because, I mean, looking at here, it is pi divided by 100, so it is 2 pi divided by 200. So, you know, 2 pi divided by 200, which means that n should be at least equal to 200. At least, the minimum. Okay? So n should be any integer multiple of 200. Now, if n is equal to 200, it's okay for the omega 2. So I need to find a solution for these two conditions. That, I mean, it's very simple for this exercise that, you know, solution is n equal 200 or any integer multiple. So 200, 400, 600, 800, and so on. Okay? So n should be integer multiple of 200. Lack of time. Let me see if there is something that I can do on the fly. Okay, so we continue on that. I don't know exactly if we continue on Friday or next week, but you know, probably it's better to continue Friday. Now, let me give you the hint for the, since we are here, let me give you the hint for the solution of the second part of the exercise. Now, what's happened is that here I'm asking you, choose n to guarantee that the standard deviation of the estimated amplitude of each sinusoid is at least below 1% of the square of the amplitude of the sinusoid. What does it mean? It means that, you know, if I increase n, okay, remember n should be multiple of 200. So I can choose 200, 400, 600, blah, blah, blah. So the more I increase n, in the parallelogram, the value of the amplitude of the sinusoid increases with n. Okay? So, you know, overall, what I have considering the sinusoid as individual, in the parallelogram, okay, I have this one, this is going to 0, so you know it's fine. Now the amplitude is a1 squared divided by 4 multiplied by n. This happens only for the sinusoid. So what's happened is that the more I increase n, the bigger gets this amplitude. And so since the sinusoid is there, when I make n very big, then you know after a certain point the sinusoid pops up. And you can see the sinusoid. This happens when, this is what we saw last time. You remember we made that simple exercise. Now you know this, when this one pops up, if I look at the sample of the sinusoid, the sample of the parallelogram for the sinusoid is very stable. So if I have only the sinusoid, you know, I have this point that pops up, gets bigger, 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 but it's very stable. It's not affected by any fluctuation because there is no random part. On the other hand, in my parallelogram, when I look at the parallelogram, I have the combination of the noise and of the sinusoid. So what's happened is that when I look at the parallelogram is affected by fluctuation, okay, and this fluctuation is dependent, so the variance of this fluctuation is sigma to the fourth power. So, you know, the variance of the parallelogram here is equal to sigma to the fourth power of W, according to the theory. Now, this fluctuation is making this point to fluctuate. And the fluctuation of that point has a variance that is sigma to the fourth power. So what I notice is that that point there, which has the amplitude of that point, which is a1 squared divided by 4 multiplied by n, okay, that is the point, the amplitude of the sinusoid, can be made bigger than this sigma squared w, which is 10 to the power 3. So this one is 1/4, so it is, this value is 1/4 times n. So if I choose n to be larger than that, I can see the sinusoid. So if 1/4 times n is larger than 10 to the power 3, subject to constraint that n is 200 times capital L, which is integer, okay? So subject to the case that n is an integer number, is an integer multiple of 200, then what I can see is that I see the sinusoid, which means the sinusoid is bigger than the floor of the noise. But since the tip of this vector, this point, is fluctuating with a variance that is as big as sigma, with a variance that is sigma w to the fourth power, so what I see is that I see this vector which is fluctuating, is getting bigger. Okay? Now, the problem is asking you, what is the value of n? Choose n to guarantee that the standard deviation of the tip of this sample is at least below 1%, so the fluctuation is 1% of the amplitude of the tip itself. So it's in by word a set of constraints which is forcing you to calculate the value of n such that the fluctuation is negligible. 1% is negligible. That's the question of the exercise. Okay? And everything rules by the fact that, you know, in the parallelogram, this tip, okay, this point here, is growing by n, but is fluctuating by sigma squared to the 4th power. So you have, you have one point, and it's like here, okay? You have this one, this is fluctuating. You know, then it's, the more you get n, the fluctuation remains the same. But you know, I mean, it's growing up. So it grows with the length of the samples that I'm using for calculating parallelogram. Okay? So what I need to do is, at a certain value of n, I can see the tip. But I don't see the tip because it's embedded in the variance of the parallelogram. But you know, at a certain point, I start to see the tip, which is going up and down. Now, it's going up and down. I mean, apparently, this up and down might be big. But if I make n very big, big enough, this fluctuation is negligible. This is what I'm asking you to compute. And you know, then when I upload the file, I put the solution for that, okay, which I have more time with it to go, okay? So you will see the solution, which is a stupid equation, which is just an inequality, okay?